good afternoon. I'm glad you've all decided to spend some of your time with us today, listening to a kind of project that I get pretty excited about. Not typically your normal stream restoration or your normal restoration of any sort, but more an ecological engineering approach where we try to take a site that's really been disturbed and layer in what we know from our environment in terms of functions and create a system, a novel system that delivers benefit. And that's what this project is about. This is Sand Seepage Wetlands is a collaborative effort between folks at Biohabitats and at a small consulting company in the Maryland area, Underwood and Associates. And it's really working collaboratively is some of the best work that I think we can do. Instead of just being in our own heads, we're challenged by our peers, and good things come from that collaborative process. So I'd invite anybody that's interested in collaborating with us to contact us about that, or if you've got other folks working for other companies that you get on with from a personality perspective, look for opportunities to collaborate. You won't be sorry. So the idea behind Sand Seepage Wetlands was to be able to take pulsed flows like stormwater runoff that typically just run through the system, do a lot of damage on the system through channel adjustment, through pollution, what have you, and use that water to better effect. I mean, if you think about it, all the stormwater that we're dealing with at one time was distilled water. It's pure water. Then once it hits the ground, coming out of the atmosphere, and even falling through the atmosphere, picks up a lot of contaminants, and that's where we need to start with that stormwater. So that first, the notion that this is about treating pulsed water, but then just deepening that a little bit, that if you have, in the project example I'm going to talk about, we had water that was coming off of about a square mile of fields that are used to raise chicken feed. So the eastern shore of Maryland is one of the more dense chicken production areas. Sorry about the dog barking in the background. So what ends up happening is farmers are raising these chicken for meat. There's an incredible density of the chicken, and they have, of course, an incredible amount of manure. And that manure is just wasted on the ground, regardless of what the plant demand for those nutrients are. They just spread that chicken waste on the ground. And the eastern shore also has a shallow groundwater table that's 1 to 2 foot below the surface. So the groundwater is contaminated with a lot of nitrates. So this is one approach to dealing with that. So this is a post-restoration image of the site. It's about 25 acres. I don't know if you can see the stippling, but that's about 8,000 Atlantic white cedar trees that were planted out there. This is what the site looked like in the pre-restoration context. An upland knoll between two tributaries of a swamp system, and they mined down to poor soils, clays, and water infiltration, and then abandoned it. And then local home builders would just dump their waste here. The local town actually used it as a municipal dump for a while. The construction equipment that was used to harvest the sand was just left to rust and rot in place. So not a good situation. And a remarkable element about this project is this was a Maryland State Highway Administration environmental enhancement project. This was not done for any kind of permit need or any kind of mitigation, the Federal Highway Administration has a grant program to allow different states to go out and do environmental improvement projects in recognition that highway development historically has caused a lot of loss of quality habitat and wetlands. So the Federal Highway Administration has made this grant program available, and this was about a $2 million grant from the Federal Highway Administration to the State Highway Administration, and that's the origin of this particular project. This is sort of a distillation of how the project works. We go into this stripped sand mine where you're looking at fine clays, very fine silts, really poor soil for veg establishment, and we place a carbon-rich layer of porous material. In this case, it was sand with about 20% shredded wood. Now, I'm not talking about compost or mulch. I'm talking about wood chips at about 80% sand, 20% wood by volume. And we lay these mounds on the ground and create these seepage reservoirs, which you see on the left-hand side of the slide, on the contour. So this is the green machine. Basically, the water that is seeping through that sand bed is being exposed to a large surface area with a lot of microbes, and it's being treated hyperreically. Those microbes have a lot of carbon in the form of those wood chips, and they're just looking for the other elements that they need, the nitrogen, the phosphorus, the potassium, et cetera, that they make their biomass from. And once that process starts happening, then you also have soil invertebrates burrowing through that, maintaining a porosity. Plus, you've got these native plants that are putting their root systems in, and the roots leak simple sugars, which are more food for that microbial community, and that just keeps the whole thing going. So here's an image of a sand seepage system with the seepage reservoir on the right in this case, and if you look, that water surface is about 18-inch higher than the water surface in the stream on the left-hand side of the slide. So the gradient is the water moves through that carbon-rich sand bed and exfiltrates cleaner into the stream. This is that same site after it's been planted in a year. This is that same site after a decade. And if you were to dig a hole in that sand path that you're looking at, you'd only go about 6 inches down before you were into flowing water. Now, admittedly, slowly flowing water, but the water is moving, in this case, from the seepage system that's on the right-hand side towards the stream that's on the left-hand side. And that path is actually maintained by people who use this. So the local community really enjoys walking out here, seeing wildlife, and enjoying themselves. This is what that seepage reservoir looked like after a decade. A beautiful peat-producing wetland system, just incredible habitat, and all kind of terrific things happening from a biological perspective. I have this image to address a common question, which is about how often you have to maintain this sand and wood chip mix. Or don't the wood chips rot? Doesn't the sand plug up with sediment? And if you look towards the top of the slide, you can see some brown sediment. So that's evidence of the bioturbation from soil invertebrates, where they're burrowing through this material, grazing on the roots, grazing on the microbial biomass, and keeping that system porous. So we haven't really had to do any kind of maintenance, which would definitely be required if this was just an inert sand cake, a filter bed. This is a living system. This shows one project, which is this 25-acre site that I showed you in the beginning. But we've used the same approach on smaller stream restoration projects, as well as on retrofitting of stormwater detention basins and retention basins. So it has a lot of applications, but we'll just stick with this sand mine reclamation. We put a riffle grade control structure in the stream at this location, which raises the water surface of the surface of the water in that stream, and then we have that water flowing out into our Seepage Reservoir, which goes around 3/4 of the site. And then the only way for that water to get out, as we've said, is either for it to flow over, and it's a level spreader in that case, so it doesn't cause erosion, and then you have a lot of water in contact with a lot of plant material, or it drains hypereically because it's at a higher elevation than the ground, so it pushes it through to get through that sand, that carbon-rich sand, into the pools. The next slide's maybe a little more, a little easier to see, but this is where we have the riffle grade control in the stream, and it backs the water up into this very long recharge bed, or seepage reservoir. The only way for that water to get out is to flow laterally through that carbon-rich sand when the water is being stripped of its excess nitrogen and phosphorus, and sediments are being trapped as well. It daylights into these surface ponds, which are connected by another riffle grade control, which sets the elevation so that this hypereic process can't just run too fast. That way we have the contact time to get the kind of denitrification that we're looking at. As the water flows through this system, it ends up being returned to the stream from which it came before it flows into the swamp system. This is what the site looked like after construction and initial installation of plants, and those gray things are 8,000 Atlantic white cedars surrounded by little welded wire herbivory protection from white-tailed deer for the most part. And you can sort of see the central collection process as well as the seepage reservoir. This is the end of the first year. You can see the Atlantic white cedar and some of the broom sedge. This is the end of year 2, and it's really starting to come alive. And then these are images from 5 years after construction. In this image, you're looking across the seepage reservoir from the upland into the big central area. And then this slide is actually looking down that seepage reservoir. And you can see how much of the seepage reservoir is now established in a lot of macrophytes, a lot of floating leaves, as well as submersed and emergent wetland species. So the really interesting part about this was how fast life returned. I mean, here's a little green heron with a frog in his mouth. That's from inside of the site in one of the volunteer trees. We've had bald eagles nesting in the adjacent upland trees. All other kind of great blue heron, great egrets, wild turkey, etc. And then when you look at the performance, now this is just for nitrogen, and it's pretty interesting that you see this was constructed in 2011, and you see almost every year, the performance in terms of the percent removal and the pounds removed gets better. I've got a call into one of the collaborators, which is the Maryland Coastal Bays, because they're the folks that are doing the monitoring to try to get the next 3 years worth of monitoring data. But unfortunately, that's going to come after this webinar. So I'm sorry about the snafu with my audio, but that's the end of my presentation. I'm happy to take any questions. Crystal?
Hey there. So, Joe, we do have some great questions here. The first one has to do with contact time. So what is the ideal contact time for water to pass through these berms?
It's a good question, and it's not one that I'm going to give you a really good answer on. I think it's a lot of it is dependent on temperature. You know, you'll hear folks talk about 6 to 12 hours is sort of ideal. When you have a lot of carbon and you have a little bit warmer temperature, I think we can get away with a faster flow. In other words, reduced contact time. But that's not really one of the engineering elements that we're sort of controlling with this approach. This is a pretty passive approach. So basically, when water is coming in under base flow conditions, we're doing a really good job of pollutant reduction. As an example, the phosphorus removal in water year 2016 to 17 was almost 60%. So that's really pretty stellar on an annual basis. But when we have storm flows, so we're getting a lot more loading, we're getting less treatment because the water is flowing through the system more quickly. And when you have this kind of a naturalized system where you're not maximizing the nutrient removal, you're optimizing some of these other wetland functions like habitat value, aesthetics, climate benefits, as well as water quality. We're not as focused on trying to maximize pollutant removal. That's my best for that question, I think.
Okay, I think there is a second part to that question, and it also has been repeated in another question. So even though I know that the removal was not the target, what would you say is maybe that upper end that you might be able to hope for on the removal efficiency? Was this system designed assuming that there might be, you know, for example, 50% removal at some future date, or is it just a little bit more experimental?
Well, it's definitely experimental, but I think we know enough about wetland treatment to have confidence that when we're looking at a 1 square mile drainage area and a 25-acre treatment area, we should be able to get up into the 50s, 50% removal.
One question that came through has to do with the land use. I think this really relates to that percent removal. Is the chicken farm still active next to the property?
Yes, and it's not just the chicken farm next to the property. It's the agricultural fields and the surface drains and the tile drains for the ag land, which has been receiving chicken manure this way. I mean, it was the easiest way to get rid of manure. Otherwise, it'd pile up and bury you, because these folks are putting millions of chickens a year through their farms. So they have been spreading manure on these grounds for 100 years. I'm guessing. I don't know that for sure, but since they've been raising chickens on the Eastern Shore. So not only is there ongoing nutrient load, but there's this pretty significant legacy nutrient load.
Okay. So another question that feeds into this data that we're able to get here, do you know how many monitoring locations there were throughout the project site?
No, so the monitoring is being done by the Maryland DNR Coastal Bays organization. So that's like a side of the Maryland DNR. And in fairness, we spend a lot of money on construction, and we don't spend near as much money on monitoring the results of some of these projects. And it's a credit to Coastal Bays, and in particular Roman Jessian, that he has been able to continue to get money made available to do this work. And this is just the nutrient work. We've also done a dam removal project that this system flows into, and he's been monitoring the fish migration through there as well. So it's an unfortunate reality that we don't put monitoring, give monitoring a higher value.
Agreed. I was impressed that you had this length of monitoring data for this project. Okay, so another question we have, is this technique applicable outside of the coastal plain? Can you, or have you used it in the Piedmont?
Yes, yeah. One of the first applications was in the Philadelphia area, where we placed this sand mound with wood chips on an existing sewer alignment, because people were walking through the woods on the sewer alignment, and the sewer alignment had some problems with moisture because it was a low spot. So we laid this sand and carbon-rich, laid this carbon-rich sand material on that, put a riffle grade control in it so that people could still, walk their strollers and stuff across a rock ford. But when it rained, the stormwater outfalls from the community would go into this area where our sand mound would backwater that and allow the water to seep through it. So that's in the Piedmont, and we've probably done 7 or 8 projects like that, small scale stormwater pond retrofits in the Piedmont. So in fact, one of our local counties is trying to get this kind of approach adopted as a stormwater retrofit BMP, just because not only does it get the improved water quality, but it lets the water out more slowly, so there's less downstream channel erosion. So that was their part of their hook.
Great, yeah, some volume control as well. So how about other contaminants? Any knowledge about this, the sand seepage berms working for reducing fecal coliforms?
Anything that slows the flow of water and increases the sort of that contact time is going to be effective for fecal coliform, for other organics. We've considered this kind of approach for a really rich nutrient outfall, like from a factory that makes the soybean tofu. They have a really strong organic demand in their wastewater, and wetlands work that way. So think about this not as being completely different than wetlands. We're building a system using the functions that wetlands deliver. We're just organizing it a little bit differently. So I'd say anything that you can use wetland treatment on, you can use this kind of an approach on.
Great. One question about the material. So was the seepage sand clean or from the site?
So the site had been mined pretty well. One of the ways that this project worked so well was the contractor that won the restoration contract had previously won a road building contract. So they had a lot of earthwork that they were doing associated with the road. And this site, because basically the previous owner had mined the sand out of it, and this restoration approach called for a 3-foot layer of this carbon-rich sand to be placed in a certain configuration. And So they were able to do that pretty effectively. This is not washed concrete sand or any kind of pure material. This is, material that's rapidly available or easily available. We call it material of opportunity. We've talked to some about using gravel from old roof treatments that in the not too distant past, you'd put your tar paper down, and then you'd put a 4-inch or a 6-inch layer of gravel over top of that, so that the sun wasn't destroying the integrity of your roof. Now they have membranes that they don't use gravel on anymore. So there's hundreds of thousands of yards of gravel in most cities that's sitting up on top of roofs that could be used in this way. So the beautiful thing about it is, because you're getting the biological process going in this material, which is going to help to maintain long-term porosity, we're comfortable with not having to use washed sand.
Great, thank you. Okay, so it looks like we have a few more questions, and it looks like we have enough time. So one question has to do with another application for this. Could you use it for river cleaning with higher peak flows? And in that situation, could you use it with check dams?
I missed the last part of that. Could you use it with?
In combination with check dams?
Yeah. I mean, this approach has also been used in a design that we call regenerative stormwater conveyance. It's not a lateral treatment process like it is in a wetland, where you have a broad, shallow layer. You have this incised gully. You can backfill the gully with this sand and wood chip mix, and then create on top of that a series of riffles and pools, which receive stormwater, and it's sort of like a losing stream initially, and you're getting the same kind of hyporheic processing. So it's great for outfall treatment, and then when you start talking about like perennial stream restoration, there are some techniques where you would create this hyporheic bed in your incised stream channel and build the flow path on top of that. Typically, that would still work, but what you end up doing is diminishing the value of that because of the groundwater. Basically your hyporheic bed would become saturated with shallow groundwater, and most of the treatment water, if you're looking at trying to treat the pulsed surface water, that would be running over top of that groundwater saturated material. Now, the trick there is floodplain reconnection, get it out on the floodplain where that greater surface area works, and then the water can actually soak in and work its way back hyporheically back into the stream, cleaner water. So yeah, every site is different, and we're only limited by our imagination.
Very true. Okay, another question about maybe rules of thumb, I suppose, with design. So the question is there a ratio of wetland to water that you followed, or did you just base the design on site conditions? And were you required to treat a specific rate or amount per year as part of a permit special condition?
Yes. So this was designed with this site in mind. There was there's no requirement for water quality treatment. This was the only requirement was create wetland out here and stabilize this sand mine, clean up the sand mine, and create a good wetland habitat there. That's the beauty of this enhancement funding from the Federal Highway Administration. By the way, this won an award from the Federal Highway Administration, and they only, I think, make 2 awards a year, and this was one of them. So they were pretty satisfied with it. I think you could make an argument for looking at your drainage area and your surface treatment area, and people in the past have done that with wetlands, but I think you end up seeing just how variable these systems are because of other factors, like the watershed draining to it and its characteristics, the temperature regime, the time of year that trying to do the treatment, because you can definitely expect different performance in the summer versus the winter with these kind of passive wetland treatment systems.
Great. Do we have time for one more, Amy? Yes, okay. Okay, so last one. What modeling tools are used for designing this approach? What detention basin retrofits? For detention basin retrofits, the designer typically needs to model changes in hydraulics. So is there any kind of hydraulic modeling that was done for this particular project or other types?
Yeah, absolutely. Yeah, you don't get permits for these kind of projects without going through the H&H modeling. Now I'm a systems ecologist. I'm not a PE. So I'm not 100% sure of what models were used, but they're pretty standard. It's the same models that we use for any kind of stream restoration or any kind of development review. So maybe Crystal, you can answer that. Yeah, HEC-RAS.
Yeah, I would assume. Yeah, that might be the most likely candidate, I would guess.
Thanks everybody for joining us at the watering hole today, and thank you, Joe and Crystal.